Here is a question that has appeared in the joint admission test for masters in the year 2022, and the problem is on the properties of the quotient group Q by Z, and it is from the group theory. This is question 19, and it is a multiple choice question for 2 marks. The given question is, consider the group Q plus, that is the group of rational numbers under addition, and its subgroup, that is the additive group of integers. For the quotient group Q by Z, we form a quotient group Q by Z. Then which one of the following is false? Which one of the following is false? We are given 4 options. Option A, Q by Z contains a subgroup isomorphic to Z plus. Option B, there is exactly one group homomorphism from Q by Z to Q plus. Yes. Option C, for all natural numbers n belongs to n, there exists a g, small g, belongs to Q by Z such that the order of g, small g, is n. Option D, Q by Z is not a cyclic group. So we have Q plus, the additive group of rational numbers, and Z plus, its a subgroup, Z plus, that is the additive group of integers under addition. Right, this is a subgroup of it. And we form the quotient group Q by Z. Q by Z is the set of all additive left cosets. Here we have considered left cosets, or you can consider right cosets throughout. So the quotient group Q by Z is the group of additive left cosets of Q by Z. Then we have to decide which one of the following 4 statements is false. That means one of them is false and the remaining 3 are true. Agreed. And it is a very important question, and this question is suitable for CSIR net examination also. We now discuss the solution of the problem in detail. We have the group Q plus and its subgroup Z plus, and we form the quotient group, and naturally Z plus, the subgroup, is a normal subgroup of Q plus, and we form the quotient group Q by Z, which is the group of all additive left cosets of Z. Left cosets of Z, that is x plus Z, x belongs to Q. Obviously, x comes from Q, and you can form infinitely many left cosets, as many left cosets as there are the elements of Q. So naturally, it will be an infinite group. Let us take x is equal to a rational number p by q, and without loss of generality, the denominator q can be taken as a natural number. In that case, small p, the numerator, will be an integer, which belongs to q. Then x plus z we have taken, the additive left coset, to the power of q. That means here power means is an additive group, therefore x plus z plus x plus z plus etc. plus x plus z q times, because it's an additive group. So this will be equal to q times of x plus z. That means q times of this additive left coset. And we know the addition and multiplication of additive left cosets. So the multiplication takes place. It will be equal to qx plus z, and q is, we have taken a natural number, qx will be p, because x is equal to p by q. So it will be p plus z. What is p? P is an integer. P plus z will be z only. That means the order of x plus z is at most q. For all x belongs to p by q belongs to the set of rational numbers. Agreed. So what is that we have proved? The order of every element of q by z is finite. It's a very important result. And this q by z stands for an example of an infinite group in which the order of each of its elements is finite. So give an example of a group which is an infinite group in which the order of each of its elements is finite. So the example is q by z under q by z, right? The quotient group q by z is a beautiful example. Agreed. Now let's get into the discussion further. Yeah, this is what we have proved, and let us take the option A. Option A says q by z contains a subgroup isomorphic to z plus. So q by z contains a subgroup isomorphic to z plus. This is in fact false. So what we will do is note that every element of z plus, first of all, note that every element of z plus is of infinite order except the identity element 0. So in this z plus, 0 is the only element whose order is finite, and the remaining every other non-zero integer is of infinite order. Please note down that. Now assume that q by z contains a subgroup S which is isomorphic to z plus. So that means what we are assuming is q by z contains a subgroup isomorphic to z plus. Let us say that subgroup as S. Agreed. So what is S? S is isomorphic to, S is a subgroup of q by z, is isomorphic to z plus, and therefore every element of S is of infinite order except the identity element 0 of S, because z plus has that type of properties. The same properties will be inherited to S also. So how many elements will be there in S? As many elements as there in Z. That means S has countably many elements of infinite order except one element 0 of S. So that means because S has so many, so S is a subgroup of q by z. Naturally q by z contains countably many elements of infinite order, and it is a contradiction to the fact q by z is an infinite group in which the order of every element of q by z is finite. But what you are saying is q by z contains countably many elements of infinite order, which is a contradiction. So this contradiction shows that your assumption that q by z contains a subgroup S isomorphic to z plus is false. So thus the option A is false. Now this question says out of the 4 options you have to find that option which is false. Fortunately, the very first option is coming out to be false. Therefore, the question is over. You can write down your answer. The answer to this question is option A. So you can say that and close it. But for our students, I will show you the remaining 3 options are true. So we will now show that the options B, C and D are true. So let us first of all take option D. Q by Z is not a cyclic group. Is it true? So obviously we know this must be true. So we have to give a proof. Q by Z, let us say, is a cyclic group. Let us say Q by Z is a cyclic group. That means if it is cyclic, that Q by Z is generated by a single element of Q by Z. Let us say that single element is X plus Z. So Q by Z is generated by X plus Z for some X belongs to Q. Agreed? Agreed. This means X plus Z generates all elements of Q by Z. X by Z, because this is a generator of Q by Z. X by Z, X plus Z generates all elements of Q by Z. That means X plus Z is of infinite order. Why? Because Q by Z is an infinite group. So that means X plus Z is of infinite order, which is a contradiction. Why? Because in Q by Z, every element is of finite order. So this is a contradiction to that fact. Therefore, our assumption that Q by Z is cyclic is wrong. Therefore, Q by Z is not a cyclic group is true. Thus, Q by Z is not a cyclic group. Therefore, our option D is true. Let's continue for the next option. The next option is option C. For all natural numbers, n belongs to the set of natural numbers, there exists a G belongs to Q by Z. G means an additive left coset belongs to Q by Z such that the order of G is n. Let n be a natural number is an arbitrary element for any element. Let us take any natural number. And now G, the additive left coset, is 1 by n plus Z. 1 by n is a rational number. So rational number plus Z belongs to Q by Z. That is a additive left coset of Z. Agreed. So now and raised to the power of n, G power n. That is 1 by n plus Z to the power of n. It is an additive group. Q by Z is an additive group. Therefore, 1 by n plus Z plus 1 by n plus Z plus etc. plus 1 by n plus Z n times will be, by the properties of additive left cosets, it is n into n times of 1 by n plus Z. N times of 1 by n is 1 plus Z. 1 is an integer. So 1 plus Z is Z. And any number less than this small n, it will not give you Z. It will not give you Z. Therefore, n is the least positive integer for which such that G power n is Z. So the order of G means 1 by n plus Z is n. So for all n belongs to n, there exists a G belongs to Q by Z such that the order of G is n. Thus, option C is true. We are now left with the last option, option B. There is exactly one group homomorphism from Q by Z to Q plus. A very, very, very important result. Very good result. Now let's see the proof. Let phi be an arbitrary homomorphism from Q by Z to Q plus. Agree. It's an arbitrary homomorphism. Now recall a result of homomorphisms. Then the order of phi of an element of Q by Z divides order of G for all G belongs to Q by Z. G here is phi of G. Phi of G means G comes from Q by Z. The order of phi of G, that means the order of the image of G of Q by Z will be in Q, divides order of G. Order of G. This is a very, very important property of homomorphisms. Agreed. Now, let G is equal to P by Q plus Z, because it is a additive left coset. G belongs to Q by Z. P belongs to Z, Q belongs to N. This is what we have been, arguing from the beginning. Be any element, arbitrarily chosen element of Q by Z. Let us now take the homomorphism. Phi of G. G means P by Q plus Z will be a rational number, that is, let us say R. R belongs to Q. Now, the order of phi of G divides order of G will imply order of phi of G. G is P by Q plus Z divides order of G, that is P by Q plus Z. So now this will imply phi of P by Q plus Z is R. So the order of R divides the order of P by Q plus Z. So the order of P by Q plus Z is Q by the GCD of P and Q. If they are relatively prime, you can directly write Q. You can directly write Q. If there is a GCD, divide by that, then the order of P by Q plus Z will be this one. And this is finite. This is also finite. So now note that in Q, 0 is the only element of Q. The others are all having infinite order. So 0 is the only element of Q whose order is finite. 0 is the only. And here a division is taking place. That means the division must be in the finite number of natural numbers. It should be. So who will be 0 of order of R? What is R? R belongs to Q. And who is that element whose order is finite? That is 0. So that means R must be 0. So therefore R must be 0. When R is 0, what is phi is doing? Phi is sending every element P by Q plus Z to 0. So phi of G is 0 for all G belongs to Q by Z. That means who is phi? Phi is a 0 homomorphism. That means it is sending every element of Q by Z to the 0 element of Q. So that there is only a trivial homomorphism, that is the 0 homomorphism is only there. That is phi is the 0 homomorphism and it is the only homomorphism. And the 0 homomorphism is the only homomorphism from Q by Z to Q plus. It's a very good result and a good proof what we have. Thus, the option B is true. So, we conclude. So, we have the options. Option A, we have shown false. B, C, D, they are all true. Therefore, the answer to this question is option A. So, that is the detailed discussion of the solution of the problem. The problem is on the properties of the quotient group Q by Z from the group theory, and it is a very important question, and this question is suitable even for CSIR national eligibility test also. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.